Heuristic improvements shrinking the search tree. In some cases, it is possible to significantly improve the constants in the algorithms. We only look at the example of vertex cover, which, despite its apparent simplicity, has a rich structure and admits many parameterized algorithms. Fixed K and consider a graph G. Now, if G does not have a vertex of degree 3 or more, then it is a fairly trivial graph consisting of a collection of cycles. For large G, such a graph cannot have a size k vertex cover, thus without loss of generality. At the expense of an additive constant factor, we will only concern ourselves with graphs with many vertices of degree 3 or greater. Now choose a vertex of degree 3 or greater, say V0. Now either V0 is in a vertex cover or all of its neighbors are. Thus we can begin a search tree with one branch labeled V0 and the other labeled the set of W1, W2, and so on until WP, where P is greater than or equals to 3, and the set W1, W2 until WP are the neighbors of V0. Again, consider the subgraphs of G not covered by the appropriate sets, the set V0 and the set of W1, W2, and so on until WP, respectively. In one, we need a size k-1 vertex cover, but in the other, we only need a size k-p vertex cover. Clearly, again, we only consider graphs where we always have a degree 3 or greater vertex in the relevant subgraph. Thus, the complexity of the search is now determined not by a tree of size big O of 2 to the k, but by a smaller one. The recurrence relation which generates the number of nodes in this new search tree is AK plus 3 equals to AK plus 2 plus AK plus 1, A0 equals to 0, A1 equals to A2 equals to 1. Here we always generate one node as k increases by 1 and we get a splitting on the nodes 3 back. To estimate the solution for this recurrence, we will try AK equals to C to the k and we want the best C. To take care of the 1 in the right hand side, let us try AK equals to C to the k minus 1. So now, we have to solve C to the k plus 3 equals to C to the k plus 2 plus C to the k, or C to the cube equals to C squared plus 1, where C equals to 5 to the 1/4. It is true that 1 plus the square root of 5 is less than or equals to 5 to the 3/4. Hence, AK is less than or equals to 5 to the k over 4 minus 1 can be verified by induction. This reasoning yields the following results. Theorem 3.8. Balasubramanian et al. Vertex cover can be solved in time big O of 5 to the 1/4 to the k times the size of G. Note that 5 to the 1/4 is bounded above by 1.5 and hence this solution is feasible for k which is less than or equals to 70. It is unknown what the best estimate for C above is. It is unclear how much better one can do than 5 to the 1/4. With a little more effort, we can reduce to C less than or equals to 1.39 as follows. Theorem 3.9. Balasubramanian et al. This is an big O of E plus 1.39 to the k times k squared algorithm to find whether in an n-vertex graph with E edges it has a vertex cover of size k. Proof. We will assume that the graph is connected and is not a single cycle. The algorithm consists of the following steps. Step 0. First, reduce the problem to the kernel. See the next section. We assume that we have the sorted degree sequence. From now on, we spend big O of n, which is big O of k squared time for each node in the search tree. Step 1. If there is a degree 1 vertex, simply get rid of it and pick its neighbor in the vertex cover. Step 2. Let x be a degree 2 vertex and let y and z be its neighbors. Out of y and z, exactly one or both or neither is in the vertex cover. If exactly one is in the vertex cover, then x has to be in the vertex cover to cover the edge xy or xz depending on whether z or y is in the vertex cover. Since x has no other rule, we might as well pick the other vertex y or z. So without the loss of generality, out of y and z, either both or neither will be in the vertex cover. Let ck be the number of nodes in the search tree. Case A. Let y and z together have at least two neighbors, a and b, say, other than x. Then branch as yz or xab, ck equals to 1 plus ck minus 2 plus ck minus 3. Case B. Y and z have together only one neighbor a. Since the graph is not a cycle, A has at least another neighbor B. Now AS is in the vertex cover or not. Then branch as YZB or AX, same recurrence. Step 3. If there is a vertex X of degree more than 4, then branch as X or ABCD. CK equals to 1 plus CK minus 1 plus CK minus 4. Repeating steps 1, 2, and 3, we will be left with a cubic graph. Step 4. Let X be a vertex with neighbors 1, 2, and 3 in any vertex cover if only two of the three vertices 1, 2, and 3 are present. Then X must be in to cover the edge. X, the third vertex. Instead, we might as well include the third vertex. So without the loss of generality in any of the vertex covers, the set 1 to 3, or the set 1, or the set 2, or the set 3, or none of 1, 2, and 3 will be there. Case A. The induced subgraph on 1, 2, and 3 is a triangle. Then the entire graph is K4, and pick any three of them in the vertex cover. Case B. The induced subgraph on 1, 2, and 3 contains a path 1, 2, 3. Then 1 and 3 have one another neighbor each, perhaps commonly say 4. Also 1 to 3 is in the vertex cover, or only 2 is in the vertex cover. So branch is 1 to 3 or x to 4. Ck equals to 1 plus 2 times ck minus 3. Case C. The induced subgraph on 1, 2, and 3 is 1, 2, and 3. 3 has two other neighbors, say 4 and 5. Also 1 or 2 must be in the vertex cover, and so 3 cannot be, if not all are there. So branch as 1, 2, 3 or x, 4, 5, ck equals to 1 plus 2 times ck minus 3. Case D. There is no edge among 1, 2, and 3. Case D. Point 1. 2 of 1, 2, and 3, say 1 and 2, share a new neighbor, say 4. If all of 1, 2, 3, the set 1 to 3, is not picked in the vertex cover, then, as we argued earlier, at most one of them will be in the vertex cover. So x and 4 must be picked in that case. Branch as 1 to 3 or x4. Ck equals to 1 plus ck minus 3 plus ck minus 2. Case D. Point 2. 1, 2, and 3 have disjoint neighbors. Here all 5 cases apply, and the recurrence is ck equals to 1 plus ck minus 3 plus ck minus 7 plus 3 times ck minus 6. One can prove by induction that 1.39 to the kth satisfies all the recurrence relations.